Good morning and welcome to Fike's web series. This is episode number 2. If anybody missed episode number 1, you'll get a link if you have registered, and along with all future episodes, you'll get a link that's a path to our website. My name is Blake Landis. I'm the National Sales Manager for Explosion Protection here in the U.S. Today we're going to be discussing dust hazard analysis, also known as DHA. Leading the discussion will be Brian Edwards. Brian's been a consultant and in the industry for plus 20 years, combustible dust and life safety. He also sits on the NFPA committee. So before we get started, if anybody has any questions during the presentation, on the right-hand side of your screen, there should be a little questions tab. If you can enter your questions and we have time left over, we'll go ahead and answer as many questions as we can. If any questions that we do not get to, we'll put on a PDF document, answer them after the webinar, and post them on our website as well. So without further ado, Brian, take it away.
Thank you, Blake. So today we're going to be talking about dust hazard analysis. We will start with a review of combustible dust hazards. Then I will cover the NFPA standards that apply to DHAs. And finally, I'll walk through how do you conduct a DHA. So what are the steps in completing a DHA and what should you expect from a DHA? So first off, when we're talking about combustible dust, what does that mean? So NFPA defines combustible dust as any particulate solid that presents a fire hazard when suspended in air, regardless of size or shape. So that last part, regardless of size or shape, that's a relatively new addition to the definition. Historically, there were some size standards. So NFPA defined it as a dust that was smaller than 425 microns. That corresponds with the US number 40 sieve. So, but they realized that there are a lot of material streams out there that will have particles larger than 425 microns that can still present a hazard in a process and can still present a fire or explosion hazard. So recognizing that, they removed that size criteria from the definition and really just focused on, can the material create an ignitable atmosphere when it's suspended in the air? What type of materials are we talking about? So it's normally any organic material, such as food, wood, plastic, etc. But it can also be some inorganic materials, such as metals, fine aluminum dust, or magnesium. Those are some other examples of inorganic materials that could be a combustible dust. Really, any material that's susceptible to oxidation, that can undergo the chemical reaction of oxidation and can burn, can be a combustible dust. And so why are we worried about combustible dust? So when suspended in air and when it's in a dust cloud, small dust particles can act much like flammable vapors and create a flash fire or explosion hazard. And the reason that occurs is because the rate of combustion of material increases with smaller particle sizes. So think about a large chunk of material. If you remember back the fire triangle from maybe we learned about in grade school, you have fuel, oxygen, and heat. With a large piece of material, if you have a large chunk or a block, you have only fuel and oxygen touching on the outer layer. So you have to burn through the outer layer to get the fuel on the inside of that chunk to be in contact with oxygen. Well, if you create small particles and you suspend that in air, then all of the fuel is ready to combust instantaneously. And when all of that energy and all of that potential heat is released instantaneously, it's going to create a much more explosive or much more higher rate of energy release and can be much more dangerous. So even normally slow burning material can create a flash fire if the particles are small enough and they're suspended in the air. And one of the greatest hazards associated with combustible dust is a phenomenon called a secondary explosion. So what this one unique hazard associated with dust is that unlike flammable gases or vapors, if there's a release of dust, there can be a slow release over time, and you can have dust accumulate in the workspace over days or weeks or sometimes even years it might take for dust to accumulate in a workplace. That's different than flammable gas. So if you have a release of flammable gas, you might have an immediate hazard. Whereas with dust, that hazard can slowly build up over years, and you can get dust accumulating on top of surfaces and overhead areas, on top of pipe runs, or on top of, on structural members. And if you have an event in the buildings that we call, say, a primary explosion, this is where you have an explosion inside a piece of equipment, that can send out a blast wave that disturbs this settled dust. And if this settled dust is disturbed and it permeates throughout a building, then that can create a much larger hazard. And when that larger dust cloud is ignited, you're going to have a significant increase of pressure inside the building, and that can be too much for the building to withstand. And you can have a catastrophic event that could completely devastate a structure and building and severely impact anyone inside. Because of these hazards, regulators knew they had to come up with something to address these combustible dust hazards. In 2008, OSHA, the U.S. Occupational Safety and Health Administration, enacted the National Emphasis Program for combustible dust. And what this did was it established criteria for compliance safety and health officers to use when they were conducting an inspection at a facility that handles or generates combustible dust. And I know 2008 seems like a long time ago, but OSHA still has this NEP in effect. A lot of national emphasis programs might come out for a year or two and then they go away, but not with combustible dust. You can still go on their website and still see that this is still an active national emphasis program. And OSHA relies a lot on NFPA standards. So they have their own standards related to housekeeping, related to employee protection and what they call the general duty clause. But they rely on the NFPA standards to identify dust hazards and also to identify feasible means to mitigate those hazards. So if facilities have not mitigated dust hazards as prescribed by NFPA, OSHA will often issue citations. And the NFPA itself, a lot of people did not pay much attention to combustible dust hazards until this national emphasis program came out. They didn't realize that NFPA had these dust standards. But actually, those standards date back to 1923, almost 100 years ago, when NFPA put a standard really focused on grain handling and agricultural operations. So these combustible dust standards have been around for a long time. They've changed a lot, but they've been around for a long time. And the requirement for a dust hazard analysis was first came out in 2015 when NFPA issued NFPA 652, which is the standard on the fundamentals of combustible dust. When it first came out, NFPA required that DHAs be performed for all new projects, and then for existing facilities, they were required to complete a DHA by September of 2018. They quickly realized that there weren't enough consultants, there weren't enough experts in the field to complete DHAs for all the facilities that required them. Initial estimates, I remember we calculated around 25,000 facilities in the US needed to have a DHA performed. And they realized that 3 years just wasn't enough time for everybody to get that done. So when they reissued the standard in 2019, they extended that deadline to September 2020. I know a lot of people still have not completed the DHA. With COVID, a lot of people did not have, the capacity to let people come on site. But, even if you haven't completed your DHA yet, you can still do that. Also in 2019, when they updated the standard, they included the requirement to review and update the DHA every 5 years. So now, whenever you complete your initial DHA and then you review it every 5 years, but you would also want to review it when processes change or when materials change. You would want to also review and update your DHA. In addition to NFPA 652, which covers every facility that handles combustible dust, there are several commodity-specific standards. So, such as NFPA 61 for food and agriculture, NFPA 484 for combustible metals, NFPA 664 for wood, and then NFPA 654, which covers really all the other materials that aren't in one of those other standards I just mentioned. So all of those commodity specific standards also included the requirement to complete a DHA. And NFPA is currently working to move all those standards because having so many standards can be a little confusing to people and it's a little excessive. So NFPA is currently working to consolidate all of those commodity specific standards as well as NFPA 652 into one standard called NFPA 660. We expect the initial draft to come out later this year and it'll be available for public comment with hopefully a final version coming out in 2023. So what is a DHA? So NFPA defines it, it's a careful review of fire and explosion hazards to determine the consequences of what could go wrong and to determine what safeguards are needed. So in general, what it means is that you review your process in your facility and identify fire and explosion hazards. You look to see what safeguards to have in place and are those safeguards enough to keep our employees safe and to maintain business continuity. A lot of people have a misconception. They think that dust testing or lab analysis is a DHA, but that's not completely true. I think that maybe the word analysis will throw some people off. They think a lab analysis is a DHA, but that's not right. We might conduct a lab analysis as part of the DHA in order to understand the properties of the material, but really a DHA is focused on the process equipment and the building compartments. And the material properties help us identify the risk and quantify the hazard, but a material analysis is not in and of itself a DHA. So who's required to complete a DHA? NFPA says anybody who manufactures, processes, blends, conveys, repackages, generates, or handles combustible dust is required to complete a DHA. There are some exemptions. So if it's a mercantile operation or facility that handles packaged powders, but they don't manipulate those, they don't open the packages, they're not exposing the dust to the work environment, they don't have to complete a DHA. And that might even apply to a manufacturing facility. So if a manufacturer who either uses powders as a raw material or manufactures powders as their finished product, they might have a warehousing operation. And as long as there's no production processes in there, as long as they're not opening the packages, then you can exclude some of these warehouses from your DHA. But you have to be careful. You have to make sure that you're really not exposing that dust or opening that dust to the environment. And also, if you've tested your material or you know your material is not combustible, you don't need to perform a DHA. So that's a common question we get is if we have non-combustible dust, you know, we're only handling limestone, do we have to perform a DHA? And the answer is no. So what type of industries do we normally prepare DHAs for? The two most common that I go to are going to be food and agriculture and wood products. So those include the majority of facilities that I've performed DHAs at, but we also work a lot with chemicals and plastics, with metal processing facilities, pharmaceuticals, and a whole host of other operations. You know, it could be biomass or power generation if they're still using coal. So anybody who is handling combustible dust or generates combustible dust needs to perform a DHA. And why do you want to conduct a DHA? So the primary reason is to make sure that your fire and explosion protection is sufficient to, most importantly, protect the employees, to protect the people who work there. We want to make sure that employees who work in a facility are able to make it home safe. And then we also want to make sure we maintain business continuity. So we want to make sure that those employees have a business to come back to tomorrow. So we want to make sure that the equipment is protected, the building's equipment protected, and most importantly, the employees are protected. Also, the DHA is going to help you identify safe modes of operation. This picture here shows Lakeland Mills Sawmill. This is in British Columbia. This was an explosion that happened many years ago, and it resulted in multiple fatalities, and it was almost identical to another explosion that happened at a different mill nearby. What happens is for a couple of decades, Canada forest had a problem with the mountain beetle, and they were killing pine trees. One estimate said that about 50% of the forest population, or the pine stock, was killed by these insects. So these trees were out in the forest, they had died, they started to dry out. If you're familiar with the sawmill, normally a sawmill is designed to process, at least on the front end, green lumber. So this is lumber that has a high moisture content. And sawdust from green lumber is not really a combustible dust hazard. And that's because it has that high moisture content. So when you try to burn it, when you try to ignite it, you have to burn off the extra moisture. And that means that it doesn't really support a fast burning rate. So it's not going to act like a combustible dust. Also, the sawdust tends to clump together, and it's not going to be suspended in air as easily as dry sawdust. Well, these sawmills, once they started processing this lumber that had been killed by the pine beetles, they started processing dry lumber, which is much more dangerous. They started processing it with equipment that was designed for green lumber, and it did not have the proper protections. It didn't have fire and explosion protection adequate to protect, to handle dry wood dust. And because of that, there were multiple incidents at these sawmills that were devastating. And so a DHA would have identified that and said, hey, this sawmill is okay to process green lumber, but you can't use this sawmill to process dry lumber unless you add additional safeguards. So this is a case where a DHA would have identified, safe modes of operation and could have informed them on what they could not do in the future. And the final reason to conduct a DHA is simple, because codes require it. NFPA standards, like I said, have required it for around 7 years, and more authorities having jurisdiction. So local code enforcement officers, the entities issuing building permits, fire marshals, more and more of those authorities are asking for a DHA, either for existing operations, and especially if you're building a new process or you're adding onto a facility and it's going to involve combustible dust, we're seeing more and more requests to turn a DHA in with the rest of your building permit package. So what are the general requirements of a DHA? So we'll talk about some of the high level requirements. So the high level goal really is to evaluate fire, deflagration, explosion hazards in a process and in the building, and provide recommendations to manage those hazards. And another general requirement of for DHAs is that they must be performed or led by a qualified person. That's someone who has a degree, special knowledge, or skill associated with combustible dust and is familiar with combustible dust hazards and has a proven record of understanding combustible dust and understanding how to mitigate the effects of it and to reduce the potential hazards. And also, the results of a DHA need to be documented. So you need to record the DHA, keep that on file. And if the DHA has recommendations, you need to come up with an action plan and document this action plan and say, how are we going to, over time, move to implement this action plan so we reduce the hazards at the facility. And what are some of the specific requirements of the DHA? So we'll go through and talk about, what does NFPA specifically require in a DHA? So really for each part of the process system and for every building compartment, every room, warehouse, or mezzanine, you have to identify the fire and deflagration hazards. So we'll talk a little bit about that. So how do you know where a fire hazard exists? So again, earlier I mentioned the fire triangle, and that's still in play. So a fire hazards exist where you have, in our case, combustible particulates, which are the fuel. You have a oxidizing atmosphere, so that's oxygen in the fire triangle, and you have a credible ignition source. So that's the heat component or energy component of the fire triangle. A deflagration hazard is going to exist when you have all the 3 components you need for a fire in the fire triangle, but then you add a 4th component, and that is a credible way of suspending those combustible particulates in the air. So if you have combustible dust, you suspend it in the air, you have it, the air is the oxygen, and then you add an ignition source, you have potential for deflagration. And then for an explosion, and this is where we get this explosion pentagon, you have all those four components needed for deflagration, but that they exist inside an enclosure. So when you have a deflagration, you have solid material that's burning and it's basically being converted to gas. So the gas is going to take up a much higher volume than the solid material. So you're turning solid into gas, and that's going to increase the volume that material, the mass of that material needs to take up more space. Then when you're burning, you're also creating heat, and heat's going to increase the volume too. So when you heat up air, the volume of that air increases. So when both of those occur, when you have solid material turning to gas and when you have air heating up, you can have extreme pressure build up. So if it's in a contained area and you're not allowing that pressure to release, you can have 8, 9, 10 times the pressure build up. So 8, 9, 10 bars, that's like 120 PSI inside a piece of equipment. And most equipment's not strong enough to contain that. And when you have that large amount of pressure build up inside a piece of equipment, then you can have a catastrophic failure, and that's what the explosion is. So when we're talking about combustible dust, the explosion is not what you would think of, say, with plastic explosives or some type of dynamite. It's the material itself is not necessarily exploding, but what you're having is the enclosure where that dust cloud is located. That enclosure explodes. So it's much like if you had a bomb made out of a pressure vessel. That's what it is. So when that enclosure catastrophically fails, you have all that pressure, all that energy release. The enclosure itself can turn into shrapnel. And that's what we're talking about with a dust explosion. So continuing on, what are more of the specific requirements of a DHA? So for each piece of equipment and every building compartment, you have to systematically go through and document, is there a fire hazard? Is there a deflagration hazard? Or is there explosion hazard? And you use those criteria that we talked about on the previous slide. And where there are fire and deflagration hazards, NFPA requires that you evaluate, what's going to happen. How is that fire, is that deflagration, how is it going to propagate through the equipment? So is it able to transfer from one piece of equipment to the next? Or is it going to move through the building? Will it go from one room to the other room? And how will that happen? So your DHA needs to identify the effects. So how is that event going to occur in your process? And NFPA also requires that you identify safe operating ranges. So where there are fire and explosion hazards, you need to know how can you safely operate that equipment. For equipment, that's going to be ranges such as, temperature range. Let's say you have a dryer. What's the maximum temperature that you can get that dryer to before it presents a fire hazard? Or, what's the maximum capacity of a vessel? Or what's the maximum material processing rate that you can safely do? What's the minimum airflow velocity you need in a duct work so that the dust doesn't fall out and clog a duct? So the DHA should identify these operating ranges. And for building compartments, the safe operating ranges are typically going to be your fugitive dust accumulation level. So this is the maximum amount of dust that should accumulate on surfaces. So maximum depth of dust that you should allow to accumulate on surfaces. So the DHA should identify that and say you need to make sure you keep dust levels below 1/16 of an inch or 1/32 of an inch. So the DHA should document that for the building compartments. DHA should also document the existing safeguards in place. So when we're conducting a DHA, we're not just coming in and looking to see what's missing. We document what's already in place. So we document where are there sprinklers? Where do you already have explosion protection? Where do you have ignition source controls in place? And what's your preventative maintenance program? What's your housekeeping schedule like? So we document the safeguards that you're already using. But then we also come up with recommendations for additional safeguards. So if there are hazards that have not been addressed, or are there places where some equipment that's not protected and there are explosion hazards, the DHA should address those recommendations as well. So I'll briefly, on this slide, I'll go through the steps in the DHA, and then for the rest of the presentation, I'm going to spend a time on each one of these steps and discuss in detail how we go through the DHA, what's the process, what are we looking at, and how do we perform the DHA. So the first step is we evaluate the materials being handled at each stage of the process. So, a lot of times you'll have material will change state through the process. Either you might be manufacturing a dust, or you might be taking a large material and making it smaller, or you might be taking dust and adding it to liquid and you no longer have dust. So you evaluate the material at each stage of the process and try to understand the properties at various points in the process. Then you want to develop a list of processes and equipment that are handling combustible dust. So everywhere in the process where you are generating or handling combustible dust, come up with a list of equipment and a list of building areas where there might be fire, deflagration, and explosion hazards. And for each of those areas that you've identified, you want to document, is there a fire, deflagration, or explosion hazard? And also you want to go through those processes and look for credible ignition sources. So as I mentioned earlier, NFPA added credible ignition source to the definition of deflagration and fire and explosion hazards. So you want to document what are the potential ignition sources in the process. And then you want to discuss what are the consequences of a fire or explosion at each stage of the process and in each building compartment. And review the safeguards in place to mitigate those hazards, and evaluate the level of risk to determine if you need to add additional safeguards. So first, you want to evaluate material properties. So the first step is going to be to identify every place in the process where dust is either handled or it's generated. Either you are processing using a raw powder as an ingredient. Maybe you're manufacturing powder through a spray drying process where you take a slurry or liquid and you create powder, or maybe you're cutting or sawing or grinding material and that's creating dust. So you want to look at all the points in the process where dust is handled inside equipment or where it can be released outside of equipment. And for each of those materials, either raw materials or the manufactured products, first step is to look at the safety data sheet. And maybe the vendor has already identified the hazardous properties of dust. Maybe they say it's a combustible dust, or maybe sometimes they'll even put some of the explosion parameters on the safety data sheet. But honestly, that's kind of rare. So oftentimes the safety data sheet might be vague. It might say it could create a combustible dust, but it doesn't really define, how much of a hazard is it. So if the safety data sheet doesn't state it, then the next place I normally go is going to be in either textbooks, online databases, or the NFPA standards themselves. So there's a lot of information out there on the combustible or on the combustion properties of common materials such as wood dust, sugar, flour. There's a lot of empirical data out there. But you might not, you might handle material in a different way that's different, or you just might not have any data out there. There might not be any published data. So if that's the case, the next step is to send the dust off for testing. So send it to a company like Fike. We have a combustion testing lab that can perform these tests. You can determine explosion severity data. So PMAX KST can give you information on, how much energy would be released and how fast would that energy be released with your specific dust, because it can vary greatly. You can have dust that produces, a KST very low, and yeah, sure, it can produce significant damage, but it's a relatively moderate hazard to something like magnesium or fine aluminum dust that can be very energetic and create a lot of energy. And then you can also have varying degrees of ignition sensitivity. So we can test for that. We can test to determine the minimum ignition energy, the minimum ignition temperature, or what concentration is required, how dense does the dust cloud have to be ignitable. So material testing can determine this data if you don't have it already. And so once you've looked at your process and you've determined which materials are combustible and which processes are creating combustible dust or handling combustible solids, Then you want to create a list. So look at a process flow diagram or P&IDs, or if those aren't available, just go out and physically look at the equipment and write a list of all the pieces of equipment where dust is handled. And you want to pay specific attention to, storage vessels, to particle size reduction equipment, to dryers and ovens and dust collectors and, conveying systems, whether it's pneumatic or mechanical conveying systems and sifters and screens. So identify all the equipment that's handling combustible dust and come up with a list. And that's going to let you know, okay, these are the pieces of equipment that I need to look at to determine if there's fire and explosion hazards. And then once you have that list, you systematically go through for each piece of equipment, you're going to look at how is the solid material being handled in that equipment. Is it being handled, is the material at a state where it's burned? It might be, start out at a high moisture content and it's not really combustible dust. And as you process it, or as you make the material smaller, or as you dry it, at different stages of the process, it might transition from a non-combustible material to combustible material. So you want to look, okay, at this stage of the process, is the material easily burned? Is it a fine, dry particle? And is it being handled in a way where you can have a dust cloud either inside that piece of equipment? For example, is it a silo and during a filling operation, you might have a dust cloud in that void space in the silo? Or if it's a conveyor, a belt conveyor, maybe in the middle of a belt conveyor, you're not going to have much of a dust cloud, but at the transition points, you have a dust cloud. So you want to look, okay, where inside the process equipment could there be a dust cloud? And you want to consider not just normal operations. You want to look at all different types of operations. You want to look at startup and shutdown. You want to look up at potential upset conditions that, maybe during normal operation, there's not a dust cloud, but if there were some process upset, if part of the piece of equipment were to break or become dislodged, you could have an upset condition that could create a dust cloud. So you want to consider all these conditions when you're identifying fire and explosion hazards. And then you also want to look at the building itself. So where in the plant, where in your process, where in the building can you have dust accumulate? And how quickly can it accumulate? Do you have a building where, over a few hours, you're going to have significant dust buildup, or is it a process where it takes years for dust to build up because there's not many open processes and all the equipment's fairly well sealed? But you want to identify those areas where you can have buildup of dust, and you want to make sure you pay attention to hidden or rarely visited areas, because there are a lot of times where you can have dust accumulation that goes unnoticed, such as in drop ceilings or in mezzanines. And then you also, when you're looking at a building, you want to consider upset conditions too. When you're looking at fire and explosion hazards in a room, you want to think about what kind of upset conditions could occur where there could be a release of dust. Are you handling bags of powder? And if a bag were to drop or it was to spill, you could have a release of dust in there. Is there equipment that's subject to failure? For example, I was at a bakery one time and we were walking through the oven room and it was spotless. So a lot of people know food manufacturers follow what's called GMP, so good management practices. It's really a food safety practice. So you want to make sure that you operate in a sanitary environment, that you keep the facility clean, just for pest control, for bacteria control, just for food safety issues. So this bakery had a very good GMP policy in place, and it was spotless. You could literally eat off the floor. So I asked them, I said, guys, is this how it normally is? Is it always this clean? Or did you clean up knowing that, the DHA consultant was coming today, so everybody, worked extra yesterday to clean it? And they said, no, it's always this clean. Well, except a couple times a year when maybe that pipe overhead breaks. Sometimes we'll plug up a pipe and it'll start leaking, or we've actually had it completely come apart and we blew flour everywhere. Well, that's important to know, because in that oven room, we had stuff like pilot lights, we had open flames. So to understand that there could be an upset condition that could release dust into this room helps us identify those fire and deflagration hazards. Here's a picture of hidden accumulation that we saw once. So this is phenolic resin dust that was accumulating in a mezzanine. Nobody ever went up there. And so the dust that accumulated like snowdrifts. So this is an example why you really, some of these places where nobody goes can be the most dangerous because you can have this long-term buildup of combustible dust that goes unnoticed or unaddressed. So once you know which pieces of equipment have fire hazards and which building compartments and which areas have, potential for to be dust being processed or handled or fugitive dust buildup, you want to look at, what are the credible ignition sources in those areas. So you look at things like process heat. So this is dryers and ovens. You look for friction. So moving parts such as bearings, or if you have conveyors, that are misaligned. You can have rubbing parts that can build up heat, frictional heat, and can be ignition sources. One important potential ignition source, especially in building units and in process equipment, is going to be from hot work. So if you're conducting maintenance activities that are creating sparks or involve open flames, such as welding or grinding or brazing, you want to make sure a hot work permit system is in place to make sure that all the dust has been cleaned up, all the combustible materials have been removed. I've seen a lot of hot work permits that, they think of combustible material means, a gas can or, pile of cardboard. But they forget that, the dust that's on surfaces or the fugitive dust, that also needs to be removed before completing hot work. Or if you're doing hot work on, duct work or a piece of equipment, you need to make sure that that equipment has had all the dust removed from the equipment, because you don't want to ignite the dust that's inside a process enclosure. I've known of fatalities that have occurred when they're conducting hot work inside a silo, for instance. Mechanical energy. So this is what we're talking about here are, moving parts, components that are adding energy to the system. So if you have metal on metal contact at a sufficient velocity, you can create sparks. So you want to make sure that any particle size reduction equipment or any blowers or fans have proper preventative maintenance programs in place. Or if you have a fan that is materials being conveyed through a blower, you want to make sure that it's made of non-sparking construction. And also foreign objects can get into the process, and those can be sources of mechanical sparks. So if you're handling a material stream that can have contamination, such as, it's common in wood products or, aggregate grain handling, where, you might get foreign objects that come from the farm or foreign objects that are, left in the tree, or, if it's downstream of mechanical equipment that's subject to failure, you want to make sure you have a way of removing foreign objects, either with magnets or screens or some type of way to get foreign objects out of the process stream. Other credible ignition sources are going to include electrical sparks and arcing, especially in rooms and buildings. If you have combustible dust potentially accumulating or being released in a room, you want to determine, is that a class 2 location? So that class 2 is defined in the National Electric Code. So class 2 is a location where you could have potential explosive atmospheres from combustible dust occurring in a room. It could be class 2 division 1, class 2 division 1 is where you commonly see visible dust clouds, or it's high potential for there being an explosive atmosphere. In those cases, you want to have dust ignition proof electrical equipment. If it's an area where, you normally don't have a lot of dust, maybe there's a little bit of fugitive dust, and maybe there's some rare upset condition that could release dust into a room, but normally it's fairly clean. That might be a class 2 division 2 location. And those areas, you just need dust tight equipment. So it'd either be identified as rated for class 2 division 2, or be a NEMA 4 or IP6X type enclosure that will be dust tight. Static electricity is a common ignition source, especially when you're conveying powders. So you can have a significant amount of static accumulation will build up. And depending on the minimum ignition energy, the static discharges can be large enough to ignite dust clouds. Radiant heat, so hot surfaces like the edge of a boiler, or a light surface might be a potential ignition source. You want to look for open flames. I mentioned earlier in that bakery, you have a pilot light. Powered industrial trucks can also be ignition sources. So if they're in a class 2 location, they need to have some type of protection from the energy source in the powered industrial trucks, whether it's the battery or whether it's a fuel system. You need to have some protection, and it needs to be a properly rated forklift or other truck. And smoking, we've gone away more. It's very rare to see a facility that allows smoking inside, but this can still be an issue. Just the other day, I found a cigarette butt in a trash can, and this was the trash can where where they put the floor sweeping. So it was a trash can full of dust, and I found a cigarette butt in it. So once you've identified the equipment where combustible dust is present and the building compartments where combustible dust can be present, and you've identified where there might be credible ignition sources, you want to look at the consequences of an event, the consequences of the fire or explosion. So you want to say, what engineering controls are in place. So if there's a fire or explosion, do we have protection on the equipment? Are there sprinklers? Is there a deluge system? Is there explosion protection already? And what type of equipment is it? Where is it located in a highly occupied area, or is it a dust collector that's located out back and it's elevated 30 feet in the air and it's not really a big hazard? So you want to consider what's the level of consequence for an event in each piece of equipment in each room. So the level of hazard is going to vary from piece of equipment and room to room based on how critical is that piece of equipment, what's it connected to, how close is it to employees, and how many people work in this room. So consider where is this hazard located related to people and critical equipment. And then you also want to see what type of equipment are connected. So a fire or deflagration, how is it going to move through the process? And what's the chain of events that are going to occur? If we have an ignition in a specific piece of equipment, where can that go? Is it going to go upstream, downstream? Is it going to vent into the room and create a potential for one of those secondary explosions that we discussed earlier? And you look at all of those. So when we evaluate risk, we look at the likelihood of an event occurring and the severity of an event. So the likelihood and the severity combine of a hazard combine to give you the level of risk. So at Fike, we use a three-pronged approach to calculating risk. So we break that likelihood component into two parts. We look at the likelihood of there being an ignitable dust cloud. Is the piece of equipment, is it a dust collector where there's always dust present? Or is there a type of equipment where, a spray dryer where you're always going to have a dust cloud and part of that piece of equipment? Or is it a conveyor that has good dust collection and you're not going to really have a big dust cloud? It's not going to be an ignitable dust cloud except during, upset conditions. Maybe you lose dust collection and allow dust to build up inside that conveyor. So you want to say, what's the likelihood of there being an ignitable atmosphere? And we rank that from 1 to 5. And the same thing with the likelihood of an ignition source. Is that ignition source always present? Is it a hammer mill and you always have the threat of, there being, a broken hammer and it creates a spark? Or is there an open flame in the room and there's always that identifiable ignition source? Or is it less likely? Is it, the only chance is maybe if the only potential ignition source is static electricity and you have bonding and grounding. So really it's only going to occur if you have some type of failure of the bond connection. Somebody forgets to rebond the equipment. That's when you might have it. So what's the likelihood of that ignition source being present? And then what's the severity? When we're looking at severity, first and foremost, it's the potential harm that can occur. How's it going to impact people? Can it cause an injury? Could it cause a fatality? Could it be a catastrophic multiple fatality event that brings up to level 5 severity? And then secondarily, what's the impact to business? Is this piece of equipment, is it a bottleneck in the process? Does every single piece of material go through this one conveyor, and if you lose that conveyor, then the plant can't operate? Or do you have redundant systems? So if you have an explosion in the dust collector and you have to repair the dust collector and replace the bags and put the vent panel back on, it doesn't really affect you because you have redundant processes. So that's going to have a less severity. And what are the existing safeguards in place? So like I said, if you have a dust collector that has explosion protection, the severity of that event is going to be lower than an unprotected piece of equipment. And so what we do is we multiply those factors together and come up with the risk ranking value. And we use that level of risk to identify, are the safeguards adequate or do you need additional protection? So, a low risk ranking value, we're going to say, okay, that's acceptable level of risk. We think you can operate this equipment safely. If there is an event, it's either not going to do much damage, it's not going to impact production, it's not going to cause any injuries, or there's just, really a low likelihood of an event occurring. As we move up, a moderate level, we might say, okay, that's tolerable level risk as long as we do have administrative practices in place or engineering controls in place to manage the hazard. So yeah, it's a moderate risk, and we think we are properly covered. Then we move up to an undesirable level of risk. Okay, this is where we start coming with recommendations. We get up to risk ranking 3, say, okay, look, we need to come with a recommendation. And as we go up 4, it's like, this is a pretty important recommendation. You need to address this as soon as possible. We don't see this much, but if we get up to, these extreme level of risk, we might say, hey, look, this is really dangerous. It's an event waiting to happen. You should probably stop what you're doing until you're able to come up with some strategy to reduce the risk. So how do we use the results of the DHA? So first off, that risk matrix, as we discussed, it's going to give you a risk ranking. It's going to determine which piece of equipment and which building compartments are currently at an unacceptable level of risk. And when you do find an unacceptable level of risk, you want to come up with recommendations that are either going to reduce the likelihood of an event, or it's going to reduce the severity of an event. So do something that's either going to reduce potential ignition sources or reduce the potential for dust cloud, or come up with some type of protective device that's going to limit the damage and reduce the severity of an event. And that risk ranking, those risk rankings are going to help you prioritize recommendations. So nobody has an unlimited resources. So if we have a list of recommendations, you can't just immediately go out and implement those. You don't have time, you don't have physical resources, you don't have monetary resources to just immediately address all the recommendations. So that risk ranking is going to help you prioritize those recommendations and help you determine what you should address first. And then, so how do we mitigate combustible dust hazard? So what recommendations are we going to come up with? So first, next week, we're going to have a entire webinar dedicated basically to this side. We're going to discuss risk reduction methods in detail on May 11th. But in general, you're going to really look at engineering controls and administrative controls. So engineering controls are going to include things like fugitive dust control. So add better dust collection system or improve the dust collection so you don't have as much fugitive dust. That's an example of an engineering control. You'll look at ignition source reduction. So you might add spark detection and extinguishing, or you have bearing monitors or belt alignment sensors. So things that can reduce potential ignition sources. And then another engineering control comment is explosion protection and isolation systems. So this will include deflagration venting, deflagration suppression, isolation and ductwork, rotary valves that act as isolation. So these are other types of engineering controls that will reduce the severity and reduce the spread of an event. Then we look at administrative controls. This is going to include your housekeeping, your maintenance, your inspection, and just safe work practices. And finally, you want to have hazard communication and training. So you want to make sure the employees understand the hazards in their workplace and to have proper training that lets them, recognize unsafe condition, and they have training on how to operate a system and training what they can and can't do, and what materials they can and can't process. So all of these things come together to help reduce the potential for a fire or an explosion hazard, and to minimize the severity of an event if it does occur. So with that, I want to thank you for your attention. Blake is going to discuss some of the questions that you have brought up. And for additional information, please visit our website, dust-hazard-analysis.com, and then our main website at fike.com. And feel free to send me an email if you have any other questions. So I'll turn it over to Blake.
Thank you, Brian. Thanks, everybody. One of the first questions that's been coming up is there going to be a link to this presentation? And yes, there has been a delay on getting the link out to you guys from last week, but it will be on by the end of this week, along with this one. So that link will take you to the website, and then from there you can view these presentations as many times as you want and share them. First question, Brian. Europe requires owners to have an explosion document. How does that compare to a DHA?
So yeah, that is first off, Jeff Davis is going to have a webinar tomorrow discussing the explosion protection documents and some of ATEX standards. So in general, what you're doing is very similar in both. So the explosion document, you're looking at, where can dust clouds exist? Where can there be explosive atmospheres? The explosion document with ATEX, first off, it's not only limited to combustible dust. You have to have an explosion document when you're handling flammable liquids and gases as well. But then another major difference is, a lot of the EPDs I've seen don't address really severity and consequence as much. They're mainly looking at where can you have ignitable dust cloud and what are the potential ignition sources and have you reduce those. They don't focus as much on, what's the potential consequences and how severe of an event it is. So that's one thing we do different when we're preparing a DHA, is that we look at those consequences in a little more detail as compared to just where can an event occur, which is what the EPD documents in Europe are often focused on. Another thing is that in Europe, it's actually regulated that the equipment manufacturers, provide safe equipment. So you'll often, either the design firm or the equipment manufacturer themselves will prepare the EPD document. It's almost standard that they will provide those to the end users. Where in the US, it's a little backwards. So it's ultimately the end user, so the facility where the process is occurring. These are the people that are expected to obtain the DHA and to find somebody to prepare the DHA for them or prepare the DHA themselves. So onus, there's still requirements in ATEX for the factory itself, but it's much more on the factories here in the US. OSHA is going to issue citation to the factory, not to the equipment manufacturer. So it's really up to the factory to make sure DHAs have been prepared.
Great. And next question is can a PSA or a HAZOP be used in substitute for a DHA?
Yes, it can. So the DHAs have those high level requirements that you have to identify fire, deflagration, explosion hazards. You have to identify safe operating ranges. But NFPA is very clear that you can use whatever method you want. You can use a HAZOP, you can use a PSA, you can use a what if checklist style process, as long as it covers those main requirements of identifying fire and explosion hazards, evaluating the current safeguards, coming up with recommendations to address any unmitigated hazards, and sort of documenting those safe operating ranges. So as long as whatever method you use covers all of those aspects, then it's fine. There's no required format. In fact, two different standards. So NFPA 652 has an example of a format. NFPA 61 has an example format. They're completely different. I'm not a big fan of either of the formats, but they clearly says you can use the method you choose.
And another question come up is an electrical area of classification a part of the DHA, or can it?
It should be. So it can be. You at least want to evaluate the hazards in a building compartment and in a room. So when I'm doing a DHA, I will state for each room in each building. I will state, you know, our opinion and how that room should be classified based on NFPA 70 and NFPA 499. So I will include that in our DHAs. The main thing that NFPA requires is you just evaluate those rooms for fire and deflagration hazards. So technically, you might not, you might be able to complete a DHA without, doing a full electrical classification, but it should, it should be something that goes along with it.
Perfect. Another question's coming up here. Can a DHA guide a customer into which method of protection to use? Are you going to notate in the DHA with which method, passive, active, is the best and most suitable for that specific application?
Yeah, so that's an important part. When you're coming out with recommendations, it's very important to understand which type of protection can be applied and which ones are going to be the most effective and the most cost effective and the safest and the most practical, because passive and active systems are going to have their time and place, depending on what type of process you have. It might be most effective to have a passive system. So in general, my recommendations, and this is just speaking for me, if you have your own consultant or if you're preparing a DHA, in general, I'm going to say, you need to add explosion protection to this piece of equipment, and then we might have an explanatory statement saying, okay, these are your options. These are the advantages of this versus that. And normally we'll add that guidance saying, these are the potential options you have, and this is, what you want to look at. So, a DHA doesn't have to, go into that detail. We normally do, but you might just say, hey, we need explosion protection. And then at that point, you can go to the vendor, say, okay, here's what we got. Help me, we need to protect it. And that, might leave it, down the road to the actual, explosion protection vendor. But, I try to recommend, which one's going to be best as part of the DHA.
And I also think it's important to note too the level of DHA that you're looking for, and that can all be done, up front. What are you looking for? Are you looking to have a, electrical area of classification noted inside of here? Are you looking for a simple gap analysis? Are you looking for product application specific? So I think that that's something that we do offer. It's just a matter of what level of detail are you looking for. That's a conversation up front between you as the consultant and the rest of our team. So. This should be a pretty quick question here. What is the main source of static in a process or a processing environment?
Yeah, so conveying of the dust is going to be the main source of static. So as you have particles that are bouncing off of each other, bouncing off the sides of equipment, you're going to get the accumulation of that static buildup. So, pneumatic systems are notorious for large levels of static accumulation. And the size of the vessel, the size of the piece of equipment is going to determine how much static can accumulate on it. So a person might be able to accumulate enough static buildup on their body to ignite a dust cloud, maybe for 40, 50 millijoule MIE, but then you get a tanker truck might be able to accumulate enough static discharge to ignite dust with the MIE as high as 400 millijoules. So, but mainly it's conveying is going to be the biggest source of static accumulation.
Okay, and one more because it's noted here several times, and it's just a general question. Does Fike have any experience with coal, and specifically coal and pulverizers, where the mills themselves, they actually are built for containment? At that point, what is the hazard? What, Brian, would you be looking for? What would you be noting on that?
So in that case, we're looking for where, if the mill itself is built for containment, where do you need to isolate it? So do you have clean air intake, or also do you have downstream equipment or upstream equipment? So you want to look at the isolation of those mills, and then you also want to consider, what type of spark detection and extinguishing may be put on the discharge of that system, and do we need to have explosion protection on the downstream equipment and isolation on all the air lines and material conveying lines.
All right, we're going to go ahead and stop it there. Once again, there'll be a link that's sent out to everybody that registered that will be for last week, this week, and all future webinars. With that, we'll have a PDF document with any questions that we didn't get to. We'll go ahead and copy, paste those into a PDF document. We'll answer all those questions, and those will go live on there as well. Thank you, everybody, for your time. Thanks, Brian.